Hello everyone, welcome to the lab 3 of ECE573 Advanced Embedded Logic Design. In the previous video, we discussed about the matrix multiplications and we discussed the slight improvement in the performance by adding the HLS pragmas, HLS pipeline pragmas in the loop 3 of the matrix multiplication. Now to improve the performance further, we need to relook at how the matrix multiplications are done. So as discussed in the previous video, matrix multiplication consists of the loop 1, loop 2 and loop 3. In the loop 1, you traverse around the row of the matrix A in each iteration. So you have for n is equal to 3, you have 3 cross 3 matrix. So in the loop 1, you go around the first iteration, you go around the row 0, then row 1 and row 2 in the third iteration. Then for every one iteration of the row loop 1, you have the 3 iterations of the loop 2 for every column. So column 0, column 1 and column 2. Then for every iteration of row 0 and every iteration of loop 2, that is loop 1 and the loop 2, you have the 3 iteration of the loop 3. And in this 3 iteration, you get the 3 subfactors, which is the 3 multiplication operation, and you club them together to get the one element of your matrix C11. And in the previous lab, what we did, we are performing only one multiplication at every at any time. And what we did, we tried to pipeline this operation so that they can be initiated much earlier than the waiting for the completion of the previous multiplication operation. And obviously, you can see that if we can parallelize this operation, so can we do this one, this one, this one in parallel? Can we do 3 multiplications in parallel? That's what we need to see. Okay, so if you want to do the 3 multiplications in parallel, and you can see that after 3 multiplication followed by the 2 addition, you need to see that you need to have the access of A11, A12, A13 simultaneously. That means you need to have the access to the entire row of the A in one go. You cannot just read one value at a time. You have to read the 3 values of A at a time. Okay. Similarly, you need to read all the 3 values of the B of the column time. Okay, then only you will be able to perform the multiplications, all the 3 multiplications simultaneously. So what does this indicate? You need to read, these values are stored in the memory and you need to read them simultaneously. That means you need to have the multiple read ports for the A, B memory. You need to have the 3 simultaneous read port, and you need to have the for A and additional 3 ports for the B. So that is the requirement. Okay, you can have 3 multipliers in parallel because that can be done in the FPGA. That's not a problem. And addition also can be done in parallel. That's not a problem. So, but the limitation is that since you are reading A values from the memory, you are reading them sequentially one after the another. So you need to modify the way you are storing the data in the memory such that you can read them in parallel. The same thing is to calculate C12. You can see that you need the entire row of the A, that is the row 0, and the column 1 of the B. So you can see that middle column you need. So basically you need one row of A and one row of B to speed up the operation further. You can go one step further, but right now we'll limit it to this level of parallelization. So in the SDSoC, your A and B matrices are stored in the memory by your processor, and then your accelerator, which is there in the FPGA, is reading this value. So the accelerator does not have any control on how the processor is storing the value and how many ports are there in the memory, because processor can store the A and B in on-chip memory, or it can store in the off-chip memory, depending upon the size of A and B. So you don't have any control where the data are stored and how much ports are there for the memory. But once A and B are copied inside the FPGA, in the internal memory of the FPGA, you have control how they can be copied. Okay, so you don't have the control how the processor copies the data into the memory, which is the DDR memory or the on-chip memory. But from there, how to copy the data into your internal memory, the accelerator has a complete control. And we to efficiently store this A, B, and the output matrix in the internal memory of the uh, uh, FPGA, so that this operation can be done in the parallel. We have the pragmas called as a HLS array partition. So HLS array partition is very important to make sure that your pipelining is done in the optimal fashion. And what is the optimal fashion? You need to make sure that your initiation interval is reduced to 1. So the pipelining is always suffer because you have the limited ports on the memory, so that you can't do the multiple read and write operations simultaneously. And whenever you have the arrays as in the memory, when you pass the arrays to the hardware accelerator, these are implemented as a block RAM. And if you study the architecture of the FPGA, the block RAM has maximum 2 ports. That means you can do only 2 simultaneous read or 2 simultaneously write operation. So if you want to do the multiple operation, for example, in the previous case, you need to do 3 simultaneously read for A and 3 simultaneously read for B. So what is the approach you need to do? You need to split the A into the multiple block RAM. And that's where this array partition comes into the picture. So for multiple simultaneous read write, array needs to be split up into the small block RAM units so that you get the multiple ports. So array partition partitions an array into the smaller array or individual element. So suppose you have this array, you can partition into the 2 array, or you can partition into the individual elements depending upon your application requirement. So it increases the number of read and write ports on the storage. For example, here you can do only 2 read simultaneously. Here you can do 2 here and 2, so 4 here. And here if you have all these in parallel, you can do all the reads simultaneously. Okay, so by using the partitioning, you can increase the number of read and write ports so that you can do the multiple read and write operations simultaneously. But you need a multiple memory. So here you can see you need only 1 block of memory. Here you need 2 block of memory of the same length, of the same size. Here the memory size of this is same as the this plus this. Okay, so the total memory requirement is not changed, but total number of different units are changing. So what is the syntax for this? You have the hash pragma HLS array partition. You need to mention the variable name which you want to partition. You need to know what kind of approach you need to use while partitioning, that is type we will discuss. You need to discuss what is the factor by which you need to partition. Like here you can see that you are creating the 2 units, so the factor is 2. Here you are creating the 8 units, so the factor is 8. So you need to explain the factor, and you need to use the dimension. For example, when you have the 2-dimensional vector, you need to indicate which dimension you want to factor. Okay, so we'll see with the example soon. So here the variable indicates the which array you want to partition. You need to give the name of that array. Then the what is the type of the partitioning, with the cyclic, block, or complete. So we'll discuss in the next slide. Factor, number of arrays to be created. Okay, and dimension in case of the multi-dimensional array. So look at the type. So we have the 3 type. Okay, so this is your input array. Okay, and you decide that I want to do the factor partitioning by the factor block. So and here my factor is 2. Okay, because I'm creating the 2 unit. So what I do, the first half of data I put it in the first one, and the second half I put it into the second unit. Okay, this is called as a block. So I take a block of data and put it in the first unit, next block of data in the second unit. Okay, if my factor is 3, then I'll take 1/3 of data, put it in the first, another 1/3 in the second, and the rest of the 1/3 in the third unit. In case of the cyclic, I go into cyclic fashion. I take the first element, I put it here, take the second element, I put it here, take the third element, I put it here, take the fourth element, I put it. So I do the division in the cyclic mode. While in case of the complete, I individually create the n registers here. So everything is independently stored. Okay, so that is called as the complete partition. So in case of the block partition, the original array is split into equally sized blocks of consecutive elements of the original array. In case of the cyclic, the original array is split into the equally sliced blocks interleaving the elements of the original array. And the complete one is to split the array into the individual element. This corresponding the memory is resolving into the register. Okay, register is the unit which stores the some n amount of bits. Okay, so next is to dimension. So for example, if you have a three-dimensional array of dimension 10, 6, 4, I can do the partitioning of each of the dimension. For example, I did do the partitioning on the dimension this one. That means I will have the 4 two-dimensional array of 10 cross 6. Okay, so you can see 4 two-dimensional array of 10 cross 6. If I do the dimension on the 1, okay, so that means this one. So I'll have the 10 2D array of size 6 cross 4. Okay, and if I do the dimension 0, that is I want to do the complete partitioning of this entire array. So I'll create a 10 into 6 into 4, that is 250 40 registers. So all the elements are separately stored. Okay, so here I need 240 memory elements. In the middle one I need 10 memory elements. In the top one I need a 4 memory elements. Okay, so this is how you can use it. So here some of the other example, here I'm doing the array partitioning on the array in with the name AB. I use the block and I use the factor 4. What do you mean by factor 4? That means there will be 4 elements, and my AB, if you see that the AB size is say 16, then first 4 will be here, next 4 here, next 4 here, and next 4 here. So I'll have the 4 factors. So this is first, second, third, fourth, and each of them containing 4 1. So in the second one, I use the factor 2 and then use the dimension 2. So if the AB is the multi-dimensional one, I can decide which dimension I will be using. And then the same one here, it is the matrix one. I can do the complete complete partitioning on the dimension 2 of this in local array, which is the 2D array. Okay, so we will be using this in our matrix multiplication one. So in the matrix multiplication, as I told you, I need to read the complete row of the A, complete column of B, and I need to store this in the actual house. So what I'm going to do, the data is stored in the processor. I'm going to copy that data inside my memory. I'm going to partition that memory such that I can do the read and write simultaneously. So what I did, I created the local array of the 1. So you can see I created the local memory for A in, I created the local memory for B in, and I created the local memory for the actual out, and it is n cross n. So what will be my next state is that I'll be doing the partitioning of this one. First thing is I'll be copying this here, all this here, and this one be here. Just I'm doing the linking between them. So first step is to copy the A in and the B in into the local A in and B in, and then partition the local A in and the B in into the A in. I need to partition in the row of order, while B in I need to partition into the column order. So you can see that the dimension for the A in will be second dimension, while the dimension for the B in will be the first dimension. So what I did the partitioning of the variable A in and B in, and then I copied the data into the local variable. So you can see that I'm copying the data. Okay, so this logic is not that difficult. I'm just copying the data into the internal memory, so you can always look at this logic and understand it in more detail. Okay, so what I did, I had the processor has stored the A in and the B in of size n cross n in the memory. I copied that into the local memory, and then I partition that memory into the dimension into the dimension 2 of the local A in and dimension 1 of the B in, so that I can read and write them simultaneously. Okay, And you need to understand I'm doing the complete partitioning. That means all the row data of the A, that is A, first row of the A or second row of the A or the third row of the A, can be loaded simultaneously. Okay. Similarly, dimension, all the columns of the B can be read or written simultaneously. Okay. So that's what I'm doing here. Then I'm doing the normal matrix multiplication, and here I'm doing the pipelining in the loop 2. Okay. Once I do the pipelining in the loop 2, if you remember in the we have written in the discuss in the HLS pipelining, if you do the pipelining in the upper loop, the lower loop gets unrolled. So what does this mean? This loop will get unrolled. And what do you mean by this loop getting unrolled? That means this operation, which we want 3 multiplication in case of n is equal to 3, can happen in parallel and then followed by the addition operation. Okay, so this loop gets unrolled because you are pipelining this loop. And then at the end, I'm copying the data from the output, local output, to the actual output 1. Okay, so this you need to understand in more detail on your own how this is done. But we have what the approach we followed. We copied the data from the processor memory to our local memory. We partition this memory such that we can read the complete row of A and the column of B, and then we utilize that in the pipeline and version, so that we can do the all the n multiplication operations in parallel, and then we copied the data back to the memory of the processor. Okay, so this is the complete code for the matrix multiplication, and we expect that we should get the improved performance. So when we tested it, you can see that in the HLS result, we got the significant improvement in latency. You can see that now my latency is only 3K. Okay, so if you look at the loop, you can see that I have 3 loops, one for the reading the data from the memory and the storing into the local data. Then I have the loop 1 and loop 2 for performing the matrix multiplication, and then I have the loop 3 for performing the write out operation inside the memory. And you can see that I am now getting the initiation interval of 1. That is the best I can achieve. And you can see that the iteration latency is this much. Okay, so the homework for you is to find out why the iteration latency is 487. Okay, so this is the homework for you, and if you can reply me back with the possible explanation and the process to what is the issue in our code, that if you remove that issue, you can get the significant improvement from this 487 to around say 200 or something. Okay, so you need to find out what is the reason I'm getting significantly higher iteration latency of 487 for matrix multiplication, and if you can give me the reason and the approach to reduce it further, you don't need to submit any homework for the rest of the semester. Okay, so this is what we got the significant improvement. And then you can see that this was with the pipelining the third loop, and this is after you do the pipelining the second loop. And you can expect that since you are doing the multiplication operation in parallel for n is equal to 32, you can see that here I need a 5 DSP48. Now since I'm doing it parallel, I need 32 into 5. You can see that it is 160 DSP units in it. And another thing is you don't need a memory here. I can see here, you can see that I need a significant amount of memory here, because I need to store them into the internal local memory. As of now, it is saying that your utilization is more than the board can afford. But after the placement route, we have tested the design is working well on the. So these are HLS are nothing but the estimates. Unless you implement on the board, you won't know whether your design can actually fit on the board or not. So this design is fortunately is able to fit on the zedboard, and it is running well. In the next video, I'll show you the comparison between the different execution time of all the different approaches on the hardware.